my congratulations. We are very happy and very pleased to have you as a doctor of this university. Thank you very much for accepting this honor for us. Thank you. Sedete.
The rector of the University of Zaragoza, the ambassador of Japan, the distinguished guests, ladies and gentlemen, I'm very much honored to be awarded the honorary doctorate of the University of Zaragoza. In particular, I'm very glad to get it this year because this year is the 400th year anniversary of cultural exchange between Japan and Spain. This man is Samurai Hasekura. Following the instruction of the Lord of Sendai in 1613, he visited Spain, and with this small boat, Samurai Hasekura left Japan in 1613 by using this small boat, and he visited Spain, and he was granted the King of Spain, the Felipe III, as an audience in 1615. So then after that, he visited Rome and returned to Japan in 1620. Okay, so now I'd like to present my work entitled Energy and Spintronics. Let me start with what energy is. Heat is the most primitive and important energy source. There's a saying, human beings has become human beings since the human beings started to use fire and heat. So heat is the most primitive and important energy source. But now there are many other energy supplies, such as electronics, magnet, electricity, electromagnetism. But heat itself is not enough as an energy. We have to convert the energies to the electricity. In 1821, Professor Zevek discovered the conversion mechanism from heat to electricity. So we call this the Zevek effect. In 1831, Professor Faraday discovered the mechanism to change the electromagnetic field to electricity. Also, in 1881, magnetocaloric effect was discovered. This is the cooling system by using a magnet. But all of them were made in 19th century. Now we are in the 21st century. So in 2006, we have discovered the conversion mechanism of the magnetic energy to electricity. This we call spin motive force. Also in 2008, we have discovered another mechanism of the change of the heat to the electricity via magnet. This is what we call spin-Debye effect. In the following, I'd like to explain this new interconversion mechanism of energy. Let me start with the spin motive force. This is the energy conversion mechanism from the magnetic energy to the electricity. Left-hand side shows the atom with the nucleus and electrons. Electron has two internal degrees of freedom. One is the charge. Charge flows, then we have an electric current. And also, electron has a spin. Spin is the origin of the magnetism. So in the usual electronics, we use the charge part of electrons, but we also like to use spin and charge on an equal footing. This is the spintronics, which I'll explain more in detail later. But spin cannot be seen because spins are random, as shown in the right figure in the material. But in certain conditions, spins align in one direction, and then we have a magnet shown in the right with N pole and S pole. Next is the conversion of energy from the electricity by motion. You see, this is the circuit, and the red and blue is a magnet, and introduce the motion magnet. Then electromotion is induced inside the circuit. So then we get electric current. This is the Faraday's effect law of the electromotive force, and this was discovered in 1831. Now, we consider a circuit made of magnet. Then, magnetic texture moves in that way. Then this motion induces the electromotion, and we get the electricity from the magnet. This is the spin motive force, which we discovered in 2007. So both electromotive force and spin motive force are quite related, we can calculate quite easily. And the bottom figure shows the electromotive force. Here, F sub E is the force acting on electron charge. For instance, this is the electric field. Then this force does the work. This is the electromotive force discovered by Faraday in 1831. In the same way, we can consider the force acting on electron spin. This is written as Fs. And this, for instance, this force is the magnetic field. And this force does the work. This is spin motive force, which we discovered in 2007. So electron has both spin and charge. Therefore, we have to combine these two effects. This is the generalized Faraday's law. So this is the example of the spin motive force. This is the magnetic wire, and arrows denote the magnetic moment. We apply the magnetic field in this way. Then this magnetic moment moves. Then this motion induces the electromotion. This blue ball is an electron. So we can get to the electric current and the voltage. This is a spin motive force which we discovered. Now, there are many possible applications of the spin motive force, and some of them are doing very well, very actively. This is the one page of the famous and the most famous textbook of physics published in 1964 by Professor Feynman. I believe Feynman is the great physicist, and I'm sure he is the next of Einstein. So by using this figure, he explained the Faraday's law of induction. At the same time, in the same page, he wrote this sentence shown by blue, namely, the modern electrical technology began with the Faraday's law discovered in 1831. So now we have a generalized Faraday law. This is really a new paradigm. Okay, now we move on to the next energy conversion mechanism, which we discovered in 2008. This is the spin-Zebek effect. Before I describe the spin-Zebek effect, I just mentioned the Zebek effect, discovered in 1831. Left-hand side shows the water, and this water is put on the fire. Then you find the bubbles. Bubbles goes up. In the same way, you put metal or semiconductor on top of fire, then electrons move up, as shown in this figure. So if you make a circuit shown in the right figure, you can get electric current from the heat. This is the Zebek effect. And this is the mechanism to convert the heat energy to the electricity. However, there are some problems of the Zebek effect. Because of the current, we have a dual heating. And so the circuit becomes hot. At the same time, the heat flowed together with the current. Therefore, the efficiency is very not so good. Therefore, this was a simple and very useful mechanism, but so far there has not been large applications yet. So now, heat. Heat, as I mentioned, heat is a very basic and primitive energy. But as we learned from the Fukushima's nuclear power plant accident, heat is sometimes our enemy. So they have to control heat. This picture shows one of the largest supercomputer recently built in Kobe, Japan. This is the computing facility and also the cooling facility. So as you see in this photo, to operate the supercomputer, we need the heating system. The size of the heating system is as large as the computing system. So we are planning to install the next supercomputer, but the most serious problem is how to control the heat when we have the supercomputer. So in that sense, we can say the heat is the real enemy of the electronics. So we have to control the heat. So the challenge of the 21st century is how to manipulate and utilize the heat energy. So spintronics, which I will explain now, is a promising candidate to overcome the heating problem in electronics devices. So now I'd like to explain the spintronics, which is my research field, in a little bit more detail. In the upper figures, there are two boards with spin up and down, and they flow together like this. Then the spin canceled. Then you have the flow of charge. This is the usual electric current. But in a certain condition, as I showed in the lower picture, when the electron propagate in a different way with the spin like that, then the charge part cancel out. Then we have just a flow of spins. This is called spin current. So the spin current has no charge flow, therefore no Joule heating. So the in the spin electrons, we utilize the spin current together with the charge current. So we have the very good energy saving devices by using the spin current, and we will show the solution to the heating problem in electronics by using spin current. The spin current and charge current can be converted quite easily. This mechanism is called spin Hall effect. You see in the left-hand side, we have a charge current, and the charge current is scattered by the heavy atoms like platinum or tungsten with this large spin-orbit interaction. Then in the perpendicular direction, we have spin current shown by red arrows. I don't go into the details, but also we can, as you see in the right figure, we introduce a spin current shown by red, and in the perpendicular direction, we get the charge current. In this way, we can convert the spin current and charge current as you like. So probably you have a microwave in your kitchen. The microwave in your kitchen, you introduce a microwave to water, and you introduce the motion, vibration of the water, and you have a hot water. This is called water resonance. In the same way, you find the magnetic resonance imaging, MRI, in a hospital. In MRI, you introduce a microwave to the body, and you excite the spin motion or spin current. Then you check your body by using the microwave. This is a MRI. In the same way, we can introduce a microwave to a magnet. And we introduce a microwave to one of the end of the magnet, as shown in the upper figure. Then you can excite the spin and spin current, and the spin current propagate to the other end. And as you see in the right lower figure, you have a blue part and the red part. Red part is the high temperature side, observed by the infrared camera. That means spin current propagate, and the spin current carry the heat, and then you get the high temperature side shown by red color. So you reverse the magnetic moment, then you have the right figure, namely the red part is in the opposite side, because when you reverse the magnetic moment, the spin current propagation is opposite, and then the heating part changes the different side. So in this way, we can excite the spin current by using microwaves, and the spin current carry the heat. So now, we can consider the opposite situation, namely, you introduce heat current, and then the heat current induces the spin current. Once we have the spin current, we can convert the spin current to the charge current, then we can get the electricity. This is the spin-Zebek effect. So we have combined our idea of the spintronics and old Zebek effect idea. Then we have discovered the spin-Zebek effect. This is in this spin-Zebek effect, we introduce the heat, and we get the spin current, and the spin current induces the electric current. So this is the device of the spin-Zebek effect. It's quite simple, and the right lower figure is the photo is the sample device which we are using in the experiment. So we have a magnet, and on top of magnet we have a metal like a platinum, and we put a voltage terminal like that. shown by V. So this device is put on the heat source. Then the heat source excites the spin current inside the magnet, and this spin current is absorbed into metal like platinum, and then because of spin Hall effect, we get a voltage. So that means heat can be converted to the electric voltage. So the important point of the spin-Zebek effect is that we can get the heat energy by using area. This is different from the usual Zebek devices in which the point is used. This means because of the magnet, we can have the film magnet, therefore we can get the area. So the power is obtained because of utilizing the area. This is a good point of our discovery of the spin-Zebek effect. Left-hand side shows the usual Zebek thermocouple, which is used so far. We have some thermocouple device, but this is a very small device. Therefore, we have to integrate, as shown in the left figure. So to get the real energy conversion, we have this kind of integrated circuit. This is quite complicated and expensive. On the other hand, as I showed in the right-hand side, we can have the film of the magnet, and on top of the magnet film, we put the usual metal, then we can get the electricity. So in this way, we can use the quite wide heat area, and we need any integrated circuit devices, therefore the cost is low. So this will be quite useful in the future application to get electricity from the heat. So far, in the beginning I mentioned that Zebek effect is quite useful, but so far there has not been large applications because of the efficiency is low. But now the thermoelectrics has revisited because of the green innovation issues. So actually the thermoelectrics Zebek effect has several advantages, namely there's just no moving part, therefore the efficiency, there's high reliability, and we can use this in any kind of the heat source. In addition, there's no production of the carbon dioxide. Therefore, this is quite environmentally friendly. Because of these advances, now the thermoelectrics has been repeated, and various application is going on. These three figures are example. In NASA, in the United States, thermoelectric generators are installed in various space shuttle and these spacecraft, such as Curiosity. And also in Japan, there are many hot springs. So Toshiba Electric Company is planning, has a project to get the electricity from the hot springs named Kusatsu. This is the middle picture. And also the several car companies want to get the electricity from the heat, and they want to improve the efficiency of the hybrid cars. So these applications are now going on. So far, the efficiency of the conversion efficiency is 10%, but the benchmark of these applications is 20%. This is the mark. So, and also we like to apply our spin-Zeebeck device to these systems. One of the examples of our application of the spin-Zeebeck effect is install this to the computer. You see, your computer becomes hot. So this is your experience. So we want to convert this energy, heat of the PC to the electricity. This is one of the possible applications we are planning. Also recently, Professor Ibara's group has developed the new spin-Zeebeck materials, which is the so-called magnetite. This is the most typical iron oxide, and this is quite common materials. So that we hope in the future we'll like to use this magnetite as the spin-Zeebeck devices. Okay, as in summary, spintronics is not just one of the electronics, but spintronics is introducing the interconversion of a variety of energies. Here, I have introduced two new interconversion mechanisms from the spintronics. One is the spin multiforce. This is the conversion from the magnetic energy to the electricity. And the other one is the spin-Zeebeck effect. This changes the heat energy to the electricity by using magnetic materials. So now, finally, I would remind you again this textbook by Professor Feynman. He says the modern electric industry started with the Faraday's law, discovered in 1831. Now, we have generalized Faraday's law and the spintronics. So we have the good time to have a new paradigm in science and technology. Thank you very much for your attention.
Profesor Maekawa, señor embajador de Japón en España.